Well, I make it 7:30. So shall we start, Mark?
Yep, why not?
Why not? Can I welcome everybody to this December meeting of the Astronomical Society of Edinburgh. The agenda tonight is, I'll say a few words and welcome a few people. Then we have our talk. And tonight, a slight departure from the norm with Horst slowly moving away from the society in a not too distant future, I understand. We thought we'd try something different in terms of the Sky and the December presentation, and we'd spread this around. So it was suggested, why don't I do it to start with? So I shall be doing the Sky in December tonight. Okay, Mark. First of all, then, we've got two new members. And if members would like to welcome Elfrida and Pat in the normal way, that'll be very good. Welcome on board. And I understand we've got about 5 Christmas gift memberships in the pipeline at the moment. So our membership now stands at 131 and still rising. So we're doing very well. Subscriptions are outstanding at the moment. So if you want to send a check or direct transfers to Alan, I'm sure he'd be welcome those with open arms. It only costs £30 to join, 15 if you're in full-time education or you're old. Or perhaps you ought to say, if you're in full-time education as a student, professors, it'll be 30. You can find out all about the Society on our website. Indeed, most of the talks that have taken place during lockdown are available on our YouTube channel, again, accessible via the website. Thank you, Mark. And coming up on Wednesday of next week, we have the Imaging Observing Group. It's a members-only session. On the 11th of December, we're going to have a Christmas virtual pub quiz. You can eat and drink whatever you want to supply, and hopefully we'll have some fun. Again, that's a members-only night. The next public engagement will be on the 11th of December, and where we've got the fastest eye on the sky about the Vera Rubin Observatory.
That's the 8th of January, actually.
Sorry.
That's the 8th of January, yeah.
It is. It's the 8th of January. And also Alan will be doing the Sky in January. That'll be followed by the Imaging Group on the 13th of January. And on the 15th, Alan will again be leading the show, where we have part of our 4 Steps to the Stars programme, part 3, which is Navigating the Night Sky. So it's aimed at beginners, learning how to navigate your way around. All are welcome, and we'll discuss that again at the next meeting. Thanks, Mark. Now, tonight's talk has generated a lot of interest. The numbers on Facebook were unusually high from what we've been experiencing in the past, and indeed the talk following is also scoring high. So we've reached, I think, nearly 45,000 now. People who are interested in the talk, and we'll see how many turn up on our YouTube tonight. So no expectations, and with that, we're going to have a talk about astroseismology and exoplanets, and we have Professor William Chaplin from Birmingham, who's going to give us a talk. Would you like to share your slides now, please?
There we go. Okay, can you hear me okay?
Fine.
Okay, well, thank you very much. And thank you, first of all, for inviting me to give this talk. So it's a great pleasure to be speaking to you tonight. The title of my talk, I'm going to be talking about our involvement in Birmingham in a NASA mission called TESS. TESS is an acronym for the Transiting Exoplanet Survey Satellite. But also as well, I'm going to be talking a little bit about the why we're involved in it, and that comes mainly through the type of science that we do. One of the sort of 2 main things that we cover is exoplanets. And the other is something called astroseismology, the natural resonances of stars. So I'll come on to explain what we mean by astroseismology, and also as well why astroseismology and the study of exoplanets go very much hand in hand. As we'll see, seismology provides us with a way to characterize the host stars around which we're discovering planets to levels of fantastic accuracy and precision. We can learn about the interiors of the host stars as well. And as we'll see, knowing as much about the host star is really imperative if you want to know as much as possible about the planets and the new stellar systems that you've discovered. So this is the focus of our talk tonight, a NASA mission that was launched a couple of years ago. This is a mission which actually went from conception to actually flying, and it's been collecting data now, science data, for over 2 years, actually quite quickly. It was a mission as well that has some very, very prominent forebears, and that's actually where I'm going to begin. So we're going to loop back to TESS in a few minutes' time, but I want to begin by talking about the legacy of this mission, Kepler. So Kepler was launched in 2009 with the prime goal of detecting potentially habitable Earth-like planets orbiting in the habitable zone of stars like the Sun. Essentially, Kepler is a great big light bucket in space, essentially. It's about the size of a bus. It has a 1 meter collecting area, and it was designed to be able to detect with some ease planets that are Earth-sized and smaller, orbiting, again, other sun-like stars, but sun-like stars in the nearby parts of our galaxy, but stars that are actually fainter than the naked eye. So the sweet spot in terms of the apparent magnitude range for these stars that Kepler was aiming at were basically targets of about 8th or 9th magnitude and fainter. So of course, this is, as you know, several magnitudes already fainter than the naked eye limit. Now, Kepler went from conception to being launched over a duration of a couple of decades. So unlike TESS, which happened very, very quickly, the Kepler mission took much longer. And that in part reflects the fact that it was just a much, much bigger mission in terms of the size of the spacecraft, but also as well the amount it cost. And it has left a huge legacy for the field of stellar astrophysics, and also beyond that, in particular, the study of exoplanets. It has discovered literally thousands of planets orbiting other stars. It's really the first mission that has produced detections in sufficient numbers that we've been able to start to grapple with the issue of how common planets are within our galaxy. Not just planets in general, but also as well planets of different sizes or different types. So we know enough from the Kepler mission that, for example, a good rule of thumb, if you look up at the night sky, all of the solar type stars up there, you ask the question, how many of them host at least one planet? A good rule of thumb is to say pretty much everyone does. So planets are ubiquitous throughout the galaxy. Also as well, it's enabled us to get the first estimates of what we call, or solid estimates, well, I say solid, okay, the first estimates, I should say, of something called Eta Earth, which is an estimate of how many planets up there might be potentially habitable. And also as well, it's led to some fantastic discoveries. Discoveries of a, for example, a new sort of class essentially of planets that are called super Earths, that are planets between the size of the Earth and sort of small or mini Neptunes that turn out to be very, very common in other planetary systems. Our own solar system is very interesting in that it does not have one of these super Earth type planets. Now, one of the other things that Kepler enabled us to do, besides finding the planets themselves, it provided wonderful data for studying stars as well. Of course, the means by which Kepler discovered planets was through something called the transit method, where you are actually discovering the planet indirectly by the effect it has on the light that you receive from the star. So essentially, you're looking for times when the planet passes across the visible face of the star, the light from the star diminishes, and that is what is called a transit. And then you wait long enough for the planet to come round again and again and again, and that tells you that you have a gravitationally bound body orbiting your star. Now, also in addition to that, in addition to looking for, again, these brightness variations due to the presence of planets, stars themselves produce intrinsic variability that tells us about not only what's happening at their surface, but also, as we will see, what's happening in their interiors. So what we have been doing in Birmingham now for many years is studying the natural oscillations of stars. And by these means, we are able to actually see inside stars, and we're actually able to build up a picture of what the inside of a star looks like. And this remains still the only way by which we can actually do this, building up, essentially doing something like the equivalent, as we'll see, of an ultrasound scan of a star. And that provides the means to be able to characterize in great detail stars that in which we're able to observe these natural resonances or pulsations. I'll go on to discuss where they come from. And that's crucial as well if our stars also turn out to host planets. Again, because we're discovering planets indirectly by the effect they have on the light from the star, if we don't know the properties of our star very well, then that will limit what we can infer about the properties of the planet that we've discovered. So let me begin by talking about the oscillations of stars. When we study these oscillations, what are they and what can they actually tell us about the stars? You might think the title of this slide is maybe a bit glib, maybe a bit of a stretch, thinking music of the stars. Okay, let me try and convince you this isn't. This is actually really what is happening in stars. They are resonating just like musical instruments. So let's take the example of an instrument, I don't know, an oboe or clarinet, as shown here on the left-hand side of the image. To play the oboe or the clarinet, you blow over the reed at the end of the instrument. The reed vibrates. That sets up changes in pressure in the air. Those sound waves then that you're creating are then trapped within the body of the musical instrument, and the instrument then you basically get standing waves, standing sound waves as a result of those waves trapped within the instrument, and the instrument resonates at its natural harmonics or natural overtones. Believe it or not, the same thing happens with a star. Now, the image on the right-hand side here is a cutaway of the inside of a star like the sun. The bright region at the center is where is the core, where we have nuclear fusion reactions that are burning hydrogen into helium and releasing the energy that powers the star. Then we've got this region here, this sort of yellowish region here, where all of that energy generated in the core of the star is transported outwards by little packets of light that we call photons. Okay, so essentially here the energy is being transported by radiation. But when in the sun we get to about 2/3 by radius of the sun, so about 2/3 of the way out from the center, we move into this region, which is shown here in orange. And this is the convectively unstable region of the star. So here, this is where a new mechanism takes over to carry most of the energy out that's been generated at the center of the star. And that is convection. So whereas with radiation, we're transporting energy through the photons, through the radiation, here in the case of convection, we're transporting energy by moving hot parcels of gas from the bottom of this zone in an upward direction. They carry the excess energy with them, and that's how we're able to transport the energy. Now, when we get very, very close to the top of the convection zone, which is very close to the visible surface of the sun, and that's what we call the photosphere. So I should add, of course, a star being a big ball of gas does not have a solid surface. So actually we define the photosphere as the surface to be the layer where the radiation has a very, very high chance basically of escaping. So the photons can escape instead of bumping into or interacting with a particle of the gas. They escape, they travel through space and come to us here on Earth then when we can detect them and actually create images of the sun. Now, just beneath the surface there, it's still convection that is carrying the dominant load in terms of the energy. And because we have these parcels of gas that are rising up and carrying their energy with them, and also as well parcels of gas that have dumped their energy and are then sinking back down, these parcels of gas then start to buffet into one another. And that creates changes in pressure in the gas and a lot of turbulence. And changes in pressure, of course, in a gas are just sound waves. So a star, like the sun, because it is very turbulent, right close to its surface, makes sound naturally. And even though a star doesn't, again, have solid edges, it's a big ball of ionized gas, the star nevertheless acts as a natural cavity to trap the sound, just like the confines, the body of a musical instrument. And just in the same way we get standing waves set up within the body of a clarinet or an oboe, here we get standing waves set up within the body of a star. Now, of course, those standing waves, they're standing sound waves. The sound waves involve compressions and relaxations of the gas. What this means then, if we have standing sound waves within the body of the star that go all the way from the surface of the star right down into the core, it means the whole of the star is going to be doing this. So because of those standing sound waves, the compressions and relaxations of the gas that is trapped, the sound waves that are then inside the star and are traversing all of the layers inside the star. And these standing sound waves are basically rhythmically moving the material right throughout the interior of the star backwards and forwards in a periodic way. That happens all the way up to the surface. So if we observe the surface of the star, this is what we see. So these oscillations that we see of the surface of the star are the visible manifestation of these trapped standing sound waves inside the star. Now, if we go back to the analogy of the musical instrument, again, if we were to record over time the sound of the musical instrument, and then we were to frequency analyze that sound, what we would see is that the musical instrument is basically producing lots of energy at a discrete set of frequencies. And these are the natural frequencies, the harmonics or overtones of the musical instrument, okay? And because those frequencies are arranged to go in direct proportion to one another in a musical instruments are designed to be harmonic, and they're designed to sound very nice, okay? So we can literally listen to them and listen to the sound produced at these discrete frequencies. Stars do kind of the same thing. Again, they're resonating because they've got sound trapped inside. The stars resonate at their natural frequencies. So you get a whole set of overtones and harmonics produced as well. Of course, we don't literally listen to the stars here, but what we do, we get exactly the same information we would if we were recording the sound of a musical instrument over time, if we actually measure these pulsations over time. So what we can do here is we can actually record the changing brightness of the star. So as the star breathes in and out, as it breathes in, it gets hotter and brighter. As it breathes out, it gets cooler and darker. So we can record the brightness variations over time, and those brightness variations have coded into them all of the information about those trapped standing sound waves within the star. And again, if we frequency analyze the brightness variations, what we see is that the star's brightness is changing at a discrete set of frequencies. And these are the natural frequencies of the star. Now, just in the same way that the frequencies, the natural resonant frequencies of an instrument tell us about its structure, its size, what's inside the instrument, which is usually air, the same is true of a star. If we can measure the frequencies at which the star is pulsating, it tells us something about the size of the star. but also it tells us something about the internal structure of the star. And those layers of a star are usually hidden from us because we're used to observing stars by detecting the radiation emitted from their surface, but we're usually used then to trying to interpret what might be happening inside the star based on the variation of that light as a function of wavelength. But here, if we realize that that light has coded into it this information from the sound waves trapped inside, we can actually peel away the outer layers of the star and actually test what is happening inside. And we can literally do the equivalent of, because here we've got sound trapped inside, we can do the equivalent of an ultrasound scan on a star. Okay, so this is an unprecedented means of actually seeing inside stars and being able to test the fundamental properties of stars, their internal structures, how they evolve over time. But it also provides an incredibly high fidelity way to actually as well measure the mass of a star and also as well its age, how old a star is as well. So this is the field that we call astroseismology. So I've mentioned here that this is in the Oxford English Dictionary. It really is, so you can go and have a look for yourself. And you can see there the definition: the study of the interior of stars by the observation and analysis of oscillations at their surface. You can see there the reference to something called helioseismology. This is when we observe oscillations of the sun. And this is actually the work that we were originally known for in Birmingham. It was my predecessors in Birmingham who discovered that the whole of the sun was oscillating in and out, like the cartoon in the figure here. And that discovery was made back in the late 1970s. And that opened up the field of helioseismology and our ability to measure the inside of the sun. And it took until the mid-1990s for people to be able to discover oscillations in other sun-like stars. And the reason for that is that these oscillations are incredibly hard to measure. So just to put things in context, when we talk about the brightness of the sun or a sun-like star changing as a result of these oscillations, the brightness changes by a few parts in a million. So these are really, really tiny changes. And it took a while for us to get to the point that we could actually robustly measure these variations in other stars. So here's actually an example of some real data on a star that was observed by Kepler that is actually a planet-hosting star. So this was the 68th planetary system to be discovered by Kepler, hence the rather unimaginative name here, Kepler 68. That's just the way the naming convention worked for the Kepler mission. And what we're showing here is the result of frequency analyzing observations of the brightness of the star as a function of time. So the brightness is varying because of these pulsations. If we now actually analyze how is the light varying as a function of frequency, remember me saying that we'd expect to get energy produced at a discrete set of frequencies, just like a musical instrument. That is exactly what we're seeing here. So think of the vertical axis as being the strength of the signal in terms of the strength of the brightness variation. The horizontal axis here is measured in frequency. So a hertz is 1 cycle per second. A microhertz is 1/1,000,000th of that, okay? And then you can see that we have this wonderful clean pattern of almost evenly separated peaks in frequency. These are the natural resonances of the star. And it sort of looks like, again, the nice, clean, even pattern of peaks that you'd expect to get from a musical instrument. This sort of noisy pedestal that these natural harmonics are sitting on, it has some contributions from instrumental noise, but a lot of this is also intrinsic to the star as well. Okay, so it comes from that noisy convection, the turbulence we were talking about earlier. This is actually the signature of that turbulence. That actually generates the sound that gets trapped in the star, that makes the standing waves, that makes the oscillations, and that's what we see here. Okay, so this is the signature of the stuff that makes the oscillations, and these are the oscillations themselves. Just to put these numbers in context, if you turn, so 1 over a frequency is a period, we can turn this into a period of minutes. This is a period of the order of a few minutes here. So our star is resonating here with a period of a few minutes, and it's doing that in many frequencies that you can see here. So let's cycle back to the planetary side of things and the method that I already alluded to that Kepler used to discover planets, the so-called transit method. This is really simple, really elegant. The idea is that if you're lucky enough to be observing a star around which a planet is orbiting, but crucially, you are observing the plane of the orbit edge on, there will be times when your planet, as it's moving, passes between you, the observer, and the visible face of the star. So here's our little planet, our little planetary disk I'm showing here with my pointer, transiting across the visible face of the star. So for the duration of time when it's doing that, if we're monitoring the brightness of the star as a function of time, we will see the brightness diminish. And this gives what we call a characteristic transit signal. And if we observe long enough, we'll see that transit signal come round again and again and again, modulo the period of the orbit of the planet. So this is how Kepler discovered literally thousands of planets orbiting other stars in our galaxy. Now, one crucial thing to bear in mind here is that the strength of this signal here, the amount by which the light level drops, that is a relative thing. So the fractional amount by which the brightness drops depends upon the size of the disk of the planet relative to the size of the disk of the star. We can in effect treat the planet like an opaque disk. So the fractional drop in the brightness of the star goes like the ratio of the areas. For something like a Jupiter-sized planet orbiting a sun-like star, that ratio of areas is about 1 in 100. So we'd expect to see a drop in the brightness of the star by about 1%. And that's a whoppingly big signal in the context of these types of data and observations. You can detect a planet, a Jupiter-like planet around the brightest star in the sky using telescopes which have an aperture which is probably similar to, I'm sure many of you on this call have your own telescopes, and I'm sure the majority of them are certainly plenty big enough to be able to detect a gas giant planet orbiting a nearby bright star. However, if we are interested in detecting small terrestrial-sized planets like the Earth, the problem then is much, much tougher. And we have to get above the Earth's atmosphere. There's no use trying to do that from the ground. The ratio of the areas then, so the disk of the Earth is about only 85 parts per million the size of the disk of a sun-like star. So you're looking then for a drop in the brightness of the star of about 85 parts per million. So that's why you have to build something like the Kepler spacecraft to get above the Earth's atmosphere. And when you do that, you then make detecting Earth-sized planets relatively straightforward. Indeed, Kepler has discovered planets that are actually only a little bit bigger than our own moon. And this really is just reiterating this point. So this is just to show you to scale here why finding something like a Jupiter-sized planet, I mean, it might not be obvious this is easy from the image on the left-hand side here. So this is drawn to scale. Here's the disk of a Jupiter, disk of something like the sun. In fact, this is an image of the sun. But here's the problem you have. If you want to try and find an Earth or Venus-sized planet, this isn't a bit of muck on the screen here. This genuinely showing you here the size of the Earth or Venus relative to the size of something like a sun-like star. So that's the challenge, but Kepler has basically surmounted that and made it possible for us to discover literally hundreds of planets that are smaller than the Earth. Now, this slide as well emphasizes the point that again, the size of that dip goes in the ratio of the area of the planet to the area of the star. If we want to know that we have discovered an Earth or Venus-sized planet, so we want to know the absolute size of the planet, we need to know the absolute size of the star as well. Remember again, that dip in light is telling us about the size of the planet relative to the size of the star. So it's no good if you have discovered a dip in the light curve observing a star if you don't know the properties of the star very accurately or precisely. So they are going to limit your ability to be able to say as much as possible about the planet you've discovered. So that sort of hammers home the reason why something like astroseismology, besides its inherent importance, and this is a lot of the work we do for understanding the evolution of stars, it really is very, very important as a tool as well for understanding stars when they turn out to host planets that we've discovered with the likes of Kepler. So know thy star to know thy planet is a really, really important maxim here. So that's the background of what we're doing, what we did with Kepler. We worked as part of a big international consortium of about 600 scientists that were using these astroseismic data to study sun-like stars with Kepler. We actually led from Birmingham the work of about 200 of those scientists who were focused on the sun-like stars. And we also led from Birmingham as well all the work that was being done with astroseismology to support all of the planet hosting stars that we discovered as well. So yeah, that was quite a fun time. I was making quite a few trips over to California to the NASA's base at Ames, which is where the Kepler mission was run from. So that was Kepler, and that's the wonderful legacy that it has left. Sadly, Kepler's still up there, but sadly it's no longer collecting data. So just over a year ago, it finally ran out of fuel, and so it's no longer taking data. However, that brings us then to its successor, if you like, the NASA TESS mission. I already mentioned that TESS went from conception to flying on a much, much quicker timescale. I think within that full period, that was within actually 10 years. And this was a mission that was actually proposed by scientists at MIT. And what they had in mind, so Kepler during its prime nominal mission was observing stars in a very, very small patch of the sky. What the MIT team had the idea to do was, why don't we do essentially an all sky survey? So rather than focusing on a small patch of the sky for a few years, what if we actually do a survey of all of the brightest stars in the sky? We collect at least 1 month's worth of data on all of those stars, and then we use that to search for planets around all of those bright stars. Now, because here we're focusing on brighter stars than we did with Kepler, the light collecting area doesn't need to be as big to get similar quality data. And so TESS is much, much smaller than Kepler. So remember I said Kepler was the size of a bus. You can see here from these two gentlemen here doing some very serious work on the TESS spacecraft. You can see here you've got something about the size of a walk-in fridge freezer with some solar panels stuck on the side. Also notice at the top here, these are the cameras, and they're actually shown a bit more clearly here on this graphic. So we've got this baffle around the outside to try and avoid stray light impinging on the cameras. And similarly, each of the cameras here has its own baffle. The cameras are about sort of 30 centimeters in size roughly, and you can see there are 4 of them. And they're arranged in such a way that at any one time, TESS is observing the brightness of stars in a strip of the sky. And that's shown here in this image. So what we have at the center of the image here, this is the little TESS spacecraft. And if you concentrate on the strip here that I'm showing here with my mouse, each of these different square regions here is showing the different field of view of each of the 4 cameras. So you can see they're designed to stack on top of one another so that at any one time, TESS is observing the brightness of stars in this strip of the sky. What TESS is designed to do is to stare at that particular strip for around about 27 days. And what it does then is to monitor, so basically it downloads an image of that region of the sky. So each of the cameras do that on a cadence of 30 minutes. So you get a 30-minute integration. For a subset of about 200 to 300,000 stars, we get a data downloaded on a 2-minute cadence. And as of just a few months ago, a subset of those stars, we can actually record their variability now on a 20-second cadence as well. At the end of that 27-day period, TESS rotates around to observe the next strip of the sky. Again, I'm showing that with my mouse at the moment. After another 27 days have elapsed, you do the next strip and so on. So basically, after about a year, you've basically covered pretty much, not quite the entire, there are some gaps, not quite the entire half of one celestial hemisphere, but not far off. And then TESS flips over and does the other celestial hemisphere. So this was the design of the nominal mission, the first 2 years of the mission. The first year would provide this record of the brightness of stars in one half of the sky, the second year, the other half. One other thing you might have already noticed from this image is that at the celestial poles, you can see all of these strips overlap. So the implication here then is that if your stars in the at the celestial poles, so be that the northern or southern pole, you'll be observed continuously for a year. And then there are regions as well, again, close to the poles where you don't get full coverage, but because these strips overlap, you'll get more than 27 days worth of data. It's only the stars that are in these regions close to the celestial equator that only get a month's worth of data. So TESS went from conception to sitting on the launch pad in 2018, again in this period of less than 10 years. We got involved in Birmingham quite early on because what we wanted to do was transplant this big astroseismic consortium of scientists that have been working on Kepler. We wanted to transplant that to TESS. So I was one of 3 signatories that set up this big collaboration that we then transplanted from Kepler over to TESS. And we set up a whole load of working groups for people to work on different types of oscillating star. So I've been running with a colleague in Hawaii the work that we've been doing on studying sun-like stars. And by the time we got to, basically spring 2018, the mission was ready to go. I'll talk a bit about some of the preparation work that we did for getting ready for, or getting science ready for the data in a moment. But I'm just going to focus here with a few slides on the launch. Some of you might have already recognized that this looks like the top of a Falcon 9 rocket. So that's how TESS was launched, at the top of a SpaceX rocket. Here's the, just to emphasize just how small TESS is. So it's a bit of overkill, actually, when you look at the size of the fairing here. This is the same type of fairing, I think, that SpaceX have been using to launch their Starlink satellites. Where those satellites use up a reasonable fraction, I think, of the volume within the fairing. You can see from the top here, here's the little TESS spacecraft. You can see using up a tiny volume of the inside of the fairing. But anyway, that's the rocket that was used to launch TESS. And I was lucky, so one of the lucky so-and-sos who got to go and actually see the launch, which was fantastic. So a lot of the people who were involved in, at NASA, the people who were involved in building the spacecraft, and some of the lucky people like me who were involved at various universities around the world with preparing for the mission, we got to go and see the launch. There's a few images here. So this is me here, and here's me again with a countdown clock. So here we are actually at one of the launch site that we were at, the viewing site, which is a few miles from the launch pad. And TESS finally went up on the 18th of April 2018. We were actually at Cape Canaveral for a few days. The first day that we were hoping it was going to be launched, and we were actually in buses on the way to the launch pad. The launch got scrubbed because of a technical fault. And we were sweating it a bit because we had all our flights booked to return from Florida back home. But there was only a 2-day delay. And unfortunately, we'd built in a bit of a buffer. So we were able to still stick around for the launch. So here are some of my pathetic attempts to actually take photographs of the launch. So you can see here the little bright light here, that's the plume of the rocket. And you can see some of the smoke at the bottom here from the launch pad. Here's a couple more of my fairly pathetic attempts to take pictures. Okay, I'm no David Bailey. Anyway, the launch for any of you who've actually seen one of these launches for real, you'll know, like me, that they're wonderful to see. I think that aside from the sound, the thing that is most striking is actually the intense brightness of the plume of the rocket. It's almost hurts to actually watch. But in addition to being wowed by the spectacle, of course, we were all a little bit nervous in hoping that the mission would go up successfully, and it did. And TESS then took a few weeks then and a couple of months actually to go through the process of getting into its science orbit, going through all the checkouts as well to collect the first image, and also as well to do all the prep and everything that got it to the point where it could start proper science operations. It was launched in April and began science operations in June, July of 2018. This is the first flight image that was taken. So remember, we've got these 4 cameras. So here they are. This is just one snapshot, one 30-minute snapshot of the sky where TESS was looking at that time. Here are the images of the 4 cameras, and then those have been shown just expanded. Just expanded to scale here around the edges. And you can see there's a huge amount of information in these images. So to extract the science, what we will do is zoom in on one of the tiny regions of one of these images where we've got light from a star that will cover a few pixels. We'll then create a mask and then record, basically integrate the light from the pixels in that mask for the star. And we'll do that for every single image we have for that particular star. So if the star's been observed for 27 days, we'll have a whole bunch of these 30-minute images spanning 27 days. For each of those images, we get this integrated measure of the brightness of the star, and that then gives us a light curve, a measure of the brightness every 30 minutes, or as I mentioned, for some of the stars, even measured every 2 minutes, spanning over the 27 days up to a year for which we've actually observed the star. And it's from that then that we can extract the science. One of the important things that we were responsible for doing in Birmingham was actually determining which of the targets we would observe beforehand at this more rapid 2-minute cadence. And that's important because if you remember back to the slide where I showed you that that sun-like star is oscillating on a period of a few minutes, you need this rapid 2-minute cadence to be able to pick up the brightness variations from the oscillations in sun-like stars. So this is actually a map in ecliptic latitude and ecliptic longitude showing all of the stars that we selected for doing astroseismology prior to the launch of the mission. And the TESS mission actually allowed us, so NASA allowed us to have quite a sizable number of guaranteed targets. So you can see here, there's several tens of thousands of targets that we were able to guarantee would be observed for astroseismology. And they have produced a wealth of data for us, okay? There's one comment as well here. You can see sort of the, here, this is the galactic plane here. One other comment I said, you should see here, this is the sparsity of targets actually in the ecliptic. And that was deliberate because during the latter few years of its mission, Kepler had been basically observing stars in the ecliptic plane. So TESS basically during its first 2 years didn't focus on those stars. So just quickly to finish up, I'm just going to show just a couple of examples of stars where we've actually got a huge amount of science out. One of them is for a naked eye star called New Indi. So this is in the constellation Indus, which is observable from the southern hemisphere. So this is sadly not a northern hemisphere star, but here is its oscillation spectrum. This star we knew beforehand was going to be a real interesting target for us because we already knew it oscillated and we already knew this star is very, very old. And in fact, we know so much about this star, and we've added to that with these seismic data, that we know enough to know this was actually a star that was one of the first stars to be formed in the Milky Way in our galaxy. However, we know also that this star, its motion through the galaxy, even though it was formed within the galaxy, its motion within the galaxy was perturbed or changed when our galaxy collided with another galaxy very, very early on in its history. And that is shown here. So the image on the right-hand side is showing what our current Milky Way looks like. And of course, the sun is hidden somewhere in there, and so is this star New Indus. But very early on in its history, many, many billions of years ago, the early Milky Way collided with a galaxy that's called Gaia Enceladus. And so a significant number of the stars that are now within the Milky Way were actually formed outside of it. But just from this one single star, we know enough about it, thanks in part to the seismology, because we could use the seismology to get a really precise age for this star. Just from that one star, we know it was perturbed by this collision, and therefore we can place limits on when this ancient galactic collision occurred. So we can learn about the history of our own galaxy just from looking at this one single star. Here's an example then. This was the first planet-hosting star that we observed where we could also measure oscillations. So here we've got the oscillation spectrum here on the left-hand side. Just a note about the frequencies here. I should perhaps also have said here as well. You can see these frequencies are in hundreds of microhertz, and that's compared to the few thousand microhertz we expect to get for a sun-like star. So these two stars here, New Indi and this particular planet-hosting star, are stars that are a bit more evolved. They're actually in what we call the subgiant phase. So they've finished burning hydrogen into helium in their cores, and they've expanded in size, so they're now about 3 to 4 times the size of the sun. So this particular star here, here is its transiting exoplanet, okay, that was discovered. And we also as well were able to discover or confirm the presence of this planet using something called the Doppler wobble method. So being able to measure the star being pulled backwards and forwards, producing this periodic signal that we see down here. So we're now starting to really delve deeply into these data that we have now. We've got over 2 years of science data. And as of this year, we now know this mission is going to be extended. So the mission is in an incredibly stable orbit. There is enough fuel there to last for at least another 20 years. We went through the process of the senior review process. So NASA has this formal process of reviewing its space science missions that are flying every 3 years. We went through this process last year, and the mission has been extended. And so we expect this to take us through, for fingers crossed and funding permitted, hopefully for at least another 10 years, possibly another 20 years of data, which will take things well past my retirement, I should add, or well, sort of roughly up to, I think. So that was all I wanted to say. Hopefully I've given you a real flavor for what we're doing with these wonderful data. Also some insights on what astroseismology is. And at that point, I will stop. Thank you. And I'll stop sharing my screen as well.
Well, thank you very much. I think shower appreciation. Excellent. Now we can take questions. If you're on Zoom in the normal way, if you want to put your questions on the chat line, if you're watching on YouTube and you have a question, you can put it in the comments section, and we'll try and get a few of those as well. And Peter, would you like to call anybody who's got any questions?
Yes, well, thank you very much for that. That was really interesting. I think Ian Smith's got in quickly with a good question. Ian, are you there? I can't see you, but oh, there you are, right?
Yes, I'm here. I was wondering a couple of things. Using sort of lucky imaging techniques, would we be able to detect these oscillations of our own star of the sun? And secondly, if there was a passing gravity wave, would the sun's oscillations be noticeably affected?
Good question. So I think for the first one, it is actually possible to measure even though the brightness variations are a few parts per million for the sun, we nevertheless can measure those from the ground, even without having to resort to something like a lucky imaging technique. Question about gravitational waves. Yeah, this is something that people have started to think about whether or not gravitational waves, also as well whether or not things like the presence of dark matter within stars might actually affect the resonant properties of those stars. Something like a gravitational wave, I guess, is something that would be is a really transient phenomenon that just passes through a region of space. And so whether or not, bearing in mind that when we're observing these oscillations, we're sort of integrating on timescales that are probably too long to show the signatures of something like a passing wave like that. So these are things that are probably not going to, because they're so very tiny, they're not going to impact on the fundamental properties or the underlying properties or conditions of your star. But nevertheless, sort of related stuff, people are trying to think about whether or not you can use these oscillations to say something about things like the presence of dark matter. So if you have dark matter at the center of these stars, for example, you might expect that to change the properties of the internal structures of your star. And then you can ask the question about whether or not that might actually, you might be able to see observational signatures of that in the data. So people are starting to think about these issues for sure, but we're probably a long way away, I would say, from actually being able to see, to reach actually definitive conclusions on those things.
Thank you.
Thanks for that. Carl, did you have a question?
Yes, thank you very much, Professor. I really enjoyed that talk. I was curious that you were showing an image with, I don't know, about thousands or tens of thousands of stars. How do you select targets without just going back to stars that you know about, or, I mean, do you just use your gut feel, or?
Yeah,
obviously there's some science guiding it.
So in terms of which stars to choose, the ones that we chose for seismology, we very much relied on the experience that we had with Kepler. So thanks to Kepler, we detected oscillations in literally thousands of stars, and that has given us the insights and experience to know which stars in principle, provided we know a little bit about the star beforehand, which
Right.
stars where we say we have some confidence that we will be able to detect oscillations. So
Right.
because the oscillation amplitudes are so very tiny, you don't really want to waste any of these valuable slots if you don't have any chance of detecting the oscillation. So it's just the legacy of Kepler, meaning that we can make an informed choice now, and that's what
you were very clear on your slide at the start, saying you need to know about the host star as well. So it's not just enough to know about. Okay, thank you very much. Thank you.
Okay, I believe we've got some questions on YouTube, but before we go there, Ramsey, you had a question. You're muted, Ramsey. Sorry.
Okay. Is that better?
Yeah, I can hear you.
Right, okay. I've worked in ultrasound nearly all my life. So I was very interested in the spectrum analysis you were doing. And I was wondering if your microfrequency frequency analysis, does it give you a unique fingerprint for each individual star? And is this giving you additional information of its chemical makeup or its physical makeup, or a bit of both?
So yeah, essentially what those frequencies are basically giving you information on essentially the hydrostatic structure of the star. So it's telling you about the run of the sound speed within the star. And also as well, actually one thing I didn't talk about as well, it also tells you about the internal dynamics. You can actually measure the rate at which different layers within the star are actually rotating or spinning. But in terms of the structure of the star, you're getting a measure of the sound speed as a function of position within the star. You ally that to a bit of knowledge about what you think the inside of a star should look like, so a bit of stellar evolution theory. And you can then unpick things like how the temperature varies inside the star. The issue of the chemical composition of the star, we don't get that information directly. So what we do is we rely on other observations that give us information about the chemical makeup of the star from looking at the different types of elements that we see in the atmosphere. And then what we can do is we can then combine that with the information that we have from the oscillations. And that's what enables us to, for example, get a picture of how the temperature varies. So the oscillation data doesn't give us a direct measure of the composition. It's really measuring essentially the mechanical properties of the inside of the star directly. That's what we're getting. Yeah.
Thanks for that. Mark, can I hand over to you for YouTube?
Yep, certainly. We have a large and interested audience on YouTube tonight, very international from all over the world. The first question from Ming is there a characteristic frequency for convection?
Oh, yeah. Okay. So it depends where in the star you're talking about. So in the case of the characteristic frequency or timescale we talk about is the timescale on which the individual parcels of gas that are transporting energy, the sort of timescale on which we see those parcels evolve and move around. So at the surface of the sun, right at the top of the convection zone, that timescale, the characteristic timescale on which this turbulence is evolving, is of order of minutes. And it's actually no coincidence then that the strongest oscillations that we see in a sun-like star also have timescales of the order of minutes. So there's a bit of a resonance there. That's where most of again, we get sort of this resonant coupling between the natural resonances of the star and these brightness fluctuations, which are exciting the sound. They're happening on a timescale of minutes. So it's no coincidence the two timescales are similar.
Okay, thank you. Georgios is asking, he thinks TESS is currently on sector 30. Now that you've got the extension, how many sectors do you anticipate getting in the future?
So TESS is extended for 3 years. And what happens beyond that remains to be seen. I think it's a surefire bet that the mission is going to be extended. Well, I was going to say at least once more. I'd say probably at least 2 or 3 times more would be my expectation. So again, each review basically resets the clock and provides the funding for another 3 years worth of observations. We're only about half a year into the extension, so we've got definitely another 2.5 years to go. It just rests on, is the mission going to continue to produce wonderful science? Yes, it is. It's not that expensive to run because it's quite a small mission. So yeah, I'd say it's going to continue for many more years to come.
Ming asks another one. How does TESS solve the blending problem since the pixel size is about 21 arc seconds, I think? There's maybe many stars inside one pixel.
Yeah, very good question. So this is a little bit tricky. So again, the thing that saves us here is the fact that TESS is looking at the very brightest stars in the sky. So once you get down to the sort of brightness level where, of course, the further you go away from us, the fainter the stars and the more stars there are. So the good news is that the nearby bright stars, which of course are sparser, there are fewer of them, this issue of having this big, what we call point spread function, doesn't really matter a huge amount. So yeah.
And I'll ask one more. Aniban asks, if a Jupiter-like planet orbits very close to the star, can it affect these oscillations through tidal effects?
It certainly can. That's a great question. So it can actually raise tides on the star and actually excite oscillations in the star. Yeah. So we do see evidence of, there are cases where we see, again, the tidal interactions between the planet and the star as well. So yes, that can happen.
Well,
there are a few others, but I think that's probably a good time to stop, I think.
That's fine. And again, thank you very much, Bill. It always amazes me listening to people like yourself and Dr. Noor Rafi about the Parker Solar Probe, how much science you squeeze out of the data. And I guess this is the trick to it all, isn't it? But again, can members please thank Bill for his presentation.
Thank you very much. Thank you again. Thank you.
There will be a small, not very expensive speaker's gift on its way to you, Bill, as a token of appreciation. Thank you very much indeed.
Okay, thank you all.
Thank you.
Thank you very much.
Thank you.
Okay, thank you.
Right, now we'll move on to the sky in December. So it's down for me to share my screen, I think, Mark.
Yep, carry on.
Can I get rid of this? Let's have a look. That one. Share. Is this going to work? You present. Are we there?
Yeah.
Excellent. We can see your screen. Thank
Excellent.
you.
Thank you very much. Well, the sky in December. A different perspective on the monthly sky presentation. As I've said, if you want the definitive version, Alan's excellent article is in the Scotsman and on our website, and please refer to that. This is just my perspective on it. And the beauty of the sky in December, I think, is there's something for everyone. No matter whether you've got binoculars, whether you're just looking with a naked eye, or you've got an observing or an imaging scope, I think it's all well catered for, subject to the weather. And one of the first spectacles we get, I think will be on the 17th of December, where we have the moon, Jupiter and Saturn all coming together, pretty low in the sky, I must say. This is at 1640 from an Edinburgh position. And within an hour, of course, they've all set. But a great opportunity for images, or if you just want to go and have a look with your eyes, or with a bit of pair of binoculars. And then, of course, we head to the winter solstice on the 21st, and then we've got the Great Conjunction, where Jupiter and Saturn get really close together, about 0.1 of a degree. But again, fairly low in the horizon, so you need a pretty clear view to take advantage of it. And you haven't got long between the sun going down and Jupiter and Saturn both sinking down at about 5:30 from Edinburgh. Now, this happens periodically, as you probably know. Saturn completes its orbit around the sun by about 12 degrees each year, Jupiter about 30. Difference between the two being 18 degrees means that in 10 years they'll be opposite one another. In 20 years they come back and join one another. It happened in 2000, but I think we're pretty close to the sun, so it's very, very difficult to observe. In fact, the last time these planets were this close was on the 4th of March, 1226. So let's hope it's a clear day for us to observe on this occasion. In fact, because you can roll back Stellarium and Safari, Sky Safari, I've wound back the clock to 1226, and it would have looked like this at 5:15 in the morning, an hour before sunrise, and you would have got Venus to boot as well. It's a shame, really shame we haven't got that this year, but anyway. If we go to Orion, as I said, there's lots to see. Orion is always a fascinating target this time of year. I'll just make a comment about two of the great stars in Orion, Betelgeuse, as I used to say, or Betelgeuse, as people like to say, and Rigel. Quite interesting and quite different. And a quick size comparison. I just popped in the sun here to give us a size comparison. And if I were to look at Rigel, you can see it's quite a bit bigger than the sun. And if I put in Betelgeuse, change. Right, why won't you move? This would work perfectly every time I've looked.
Exit the presentation, Andrew, and go and start it again, maybe.
All right, let me just stop sharing a second. And maybe it is. Right, I'll start sharing again. See if we can get that. My apologies. Find Zoom. Share screen. Share. Share. Present. Oh, got there anyway. So So we get to Betelgeuse. So if the sun has a circumference of 4.3 million kilometers, this Betelgeuse is slightly bigger at 3.8 billion. Rigel, of course, is not just a single star. It has four components, A being the largest, BA, B, B and C, very closely bound to Rigel A. So you'll never differentiate that with your telescope, but it is four elements there. If we were to look at them and they had similar densities, you'll see they're not too different in size. So both Rigel and Betelgeuse are very puffed up stars. So the glory that is Orion, so if you take this, the view we saw before of Orion, I focused in on this area here, and Alnitak, the last star in the belt. Right next door, we have the Flame Nebula, we have the Horsehead Nebula, and in the Sword, we have the Running Man and the magnificent Orion Nebula. A great target for binoculars. I think you'd struggle with some of these, but fantastic opportunity to see these during December. And I think they're probably at their highest around mid-December. So if anybody's interested in the imaging group, I'm quite happy to have a competition for images of the Running Man, and we'll try and give a small prize in January to the one selected to be the best. And here's some images taken previously. There's one of Peter's from last year of M42, a view of the Running Man, which I took about a year or so ago, and one I think this year from Mike McGuffin of the Flame and Horsehead Nebula. Looking a bit further southeast from Orion, it's still there, over towards Gemini and Castor and Pollux. There's a great opportunity if you've got no equipment whatsoever, maybe a deck chair or a sun lounger, to see meteor shower. We have between the 4th and the 17th of December, the Geminids, where the radiant will come out from Castor. So you should be able to look in most parts of the sky and hopefully see some of the Geminids with an ideal rate of 120 an hour. Clearly we don't get that, but they're usually quite a good display. The Leonids are probably mixed in amongst that from over here. There are others, but they're either at the wrong time of year, or you've got rates of about 1 or 2 an hour, so we won't worry about those. But Geminids certainly worth looking at. If you can point a wide angle lens at the sky, take a long exposure, you may even catch some trails. Moving around to the north, to the Plough, which I've shown here, we can look up towards M81, and there's some, as always, some great globular clusters. These are a bit low down at this time of night at 9 o'clock, but a bit later they'll be even higher. And these globular clusters should be visible with binoculars. But certainly Bode's Galaxy, you wouldn't get any detail. And there's some images we've taken in the past. Looking northwest, there's a whole host of objects that we might want to observe. From the Crescent Nebula, Dumbbell, and the Ring Nebula. If I pop on some images that we've taken, we've nothing in the Flickr page. The images might want to note we've nothing for M71, so there's a gap in the repertoire. Here's a picture of the Crescent Nebula, the Dumbbell Nebula, M56, the globular cluster, and the Great Ring in Lyra. And looking west, again, some binocular opportunities, if that's what you have. There's a double cluster in Perseus and Andromeda. If you want to find the double cluster, if you look for the W of Cassiopeia and go down this leg, it should get you in the right region. If you're looking for Andromeda, The classic route is to find the square of Pegasus and then out along this line of stars, which is fairly prominent. Look for the second one. Oh, sorry, go back. Look for the second one and go up, and it should take you to M31. And here's an image of the double cluster, and you'll get a sort of shadow, a bright shadow of Andromeda in the sky through binoculars. And here's some images that have been taken by Society members during November. So Will, with his camera and a 90 times zoom, managed to get this cracking shot of the moon. And Ian managed to get one of the Lagoon Nebula. He was also busy with the Bubble Nebula and the Pleiades. Great shots. Jonathan just took his camera and tripod into an area of dark sky and managed to get some pretty wide shots of the Milky Way. Nigel got the Pac-Man Nebula, and Ian, using the same sort of palette, I think, managed to get part of the Ghost Nebula. Some sunspots, yes, we're out of the minimum, and we're now getting some sunspots. Matt caught these on the beginning of November. And I, more as a test for some equipment issues I've had, took the Triangulum Galaxy M33, and I have actually put this through a program called Topaz Denoise, which is a topic, I think, for conversation at the next imaging group meeting. Nigel also got one of the targets I mentioned before, the Flame Nebula and the Horsehead Nebula, and also the Rosette Nebula. Mike McGovern's been focusing on the moon. I think he's building a large mosaic. And Mark has had an excellent series looking at Mars through September and November, both from the polar caps. We can see Olympus Mons and the dust storm. The dust storm we can see on this part of Mars. So an excellent series of images there. So that's my quick view of the sky in November. As I say, a more definitive version, look at our website, read Alan's notes. And other than to say that what's coming up, which we mentioned at the beginning of of tonight's talk, that's it for tonight's presentations. Thank you very much.
I think we should say thank you to Andrew for that.
On the camera.
Yeah, thanks, Andrew.
Thank you.
Thank you, Andrew.
It's set a high bar.
There is a question for you from Graham Rule, asking whether you use the Gregorian or Julian calendar.
I thought somebody would ask, and I thought two people might ask that. And Graham was one of them. It is the calendar of today, Graham. I didn't go back.
Very good.
The wonders of going back to 1226. So.
Well, surely that's a non-question, because at that time it was a Julian calendar, even if it's a Gregorian that you're using. They're identical at that time.
Thank you, host.
Very good.
You've got us all scratching our heads now.
Thanks very much, guys. Thank you.
That's all right.
Thanks very much. Bye.
Thanks, Andrew.
Nice.
Bye-bye.
Bye, thanks, Al.
Excellent talk. Thank you very much. Cheers. Bye.
Cheers.
Thank you.
Okay.
Yeah, talks were all very good. Thanks.
Thanks. Me as well.